Hi, everybody. Can you guys hear me? Okay, good. We'll just wait till it becomes 2:35 and let a few more people come in, or give people some more time to come in, rather. So at the beginning of lecture, Tommy's going to take over for a while. But before, thank you, Tommy, for volunteering to go first during lecture. Very, very brave. Um, uh, Before we start, though, does anyone have any questions? Before I turn over the class to Tommy for a bit. Tommy, are you all set? You can.
Yeah, I can screen share.
Okay. All right. Tommy's going to take over for a little bit, and she's going to open up the class too.
Okay, yeah, so I'm going to be presenting on the fair kernel and specifically why it's a good kernel. You can all see that, right? Okay.
Yeah.
So remember that we were talking about kernels in relation to convolutions, right? Sorry about my handwriting. Which, as we remember, is given by this integral. And we thought of it as like the weighted average of f on the circle, where like g is providing the weights. And so what was really good, really important to us, was this specific convolution of the partial sums of the Fourier series, which is equal to f with the Dirichlet kernel. And so about good kernels, the reason why we care about them is because of this theorem saying that if the family is good and f is integrable on the circle, then all of this implies that the limit of this convolution of f with the kernel as n goes to infinity, that is just the function, so that you can like recover the function. And so we would want to know if like the Dirichlet kernel is a good kernel, right? Because that would say that all of the partial sums converge. And so remember that the good kernels had to satisfy these three properties. So this being the first one, that it has the average value on the circle of 1. The second one is that the absolute value inside the integral is bounded as n goes to infinity. And so you know that the first property of the good kernels automatically implies the second property if the kernel is positive everywhere. And then there's the third one, that if you move x away from 0, then as n goes to infinity, the kernel goes to 0. So it's like all of the mass is like shoved towards 0 as n goes to infinity. And so about the Dirichlet kernel, right, we saw that this was a no for good kernels, because even though it has the first one, we proved in homework that it's always greater than some like c log n, so it definitely doesn't have the second one. And the reason why it has the first one and the second one, which we went over, and sorry, the first one and not the second one, was because of that the kernel can be negative at some points, and so you have these oscillations of negative and positive that cancel each other out. And so that's why the absolute value of it is not bounded. And so then we have something kind of surprising, right? Even though that the Dirichlet kernel itself is not a good kernel, actually the fair kernel, which is defined as like the averages of the Dirichlet kernel, is in fact a good kernel. And so that's kind of surprising. Oh, sorry. N of x. Right, and so we're going to prove that the fair kernel is a good kernel. To help with that, in homework we made a representation of the Dirichlet kernel in terms of signs, like a fraction of signs. And so if we do the same thing for the fair kernel, then we can kind of see like what's going on with it, like if it's positive or no. And so this is not very elegant. It's just the proof that the book suggested using the geometric series. This fact that if you make this substitution, we did in homework last week, that you get this fraction. Right, and so then you move the n over for now. You can start like simplifying the fair kernel. So by formula of finite geometric series, to this fraction here, multiply it top and bottom by omega and then combine the fractions. And so after you do that, you should get something like, this is negative n plus 1. N plus 1. See that the numerator has like an extra omega, right? And so if you take that out and then you can factor the numerator. Oh, sorry, it should be omega there. Yeah. Yeah, this is just factoring it. Right, and so now we want to do the same thing for the bottom, right? Because we are thinking that we want something kind of like sine 1/2. And so we have that already at the top with the n over 2's. But we want the denominator also to have some sort of like omega to the 1/2 thing going on. And so if you take this fraction and multiply it top and bottom by omega to the negative 1, which you can also write as like omega to the negative 1/2 raised to the 2, and then refactor this denominator, then just keeping the numerator as it is. After you make that change and you factor the denominator, you have that omega like to the 1/2 that we wanted, right? And so this, like remembering the substitution, right? This is like negative 4 sine squared n over 2x, space, and then another negative 4 sine squared just 1/2 x. And so all of these things imply that the fair kernel is equal to 1 over n sine squared n over 2x over sine squared 1/2 x. Right, okay, so now that we have this, like the three properties of good kernels are gonna follow like pretty quickly. So the first one about it having an average value of 1 on the circle, since this is like the averages of the Dirichlet kernels, it's kind of like an average of an average, so you would expect it to be 1. If you just like wrote it out though, you can switch because it's like finite sum. Oh, sorry, it should be 1 over.
Yeah, 1 over n.
Yeah. Let's put the 1 over n here. Right, so we know that this is 1 from last week, and so then you have like all of these n's adding up times 1 over n, so that's also 1. And so then you have that this first property is good. Okay, so for the second property, if you look back up at the sign representation, right, this is never negative, because you have like the sign squared. So that means that this first property is going to automatically imply the second property, that the like absolute value is bounded there. So then we just have to do the third property. So for that, we notice that like this numerator is always less than 1. And then if you're away from 0, then the denominator is not going to be 0, right? Because it's 1/2 x away from 0. And so it's going to be greater than some like constant like c delta, which is greater than 0. And so then you have that this integral away from 0. That's just going to be like 1 over n, like times the c constant is like less than that. Oops. And so that's going to go to 0 as n goes to infinity, right? And so we have like all of these three are good. And so then it's a good kernel. And what's really good about like this result, right, is that since we know that this is a thing, this convolution, then you have that this, if you take the like averages of the partial sums, then it's going to be this with the convolution of the ferrokernel. And so that's an interesting thing. And so yeah.
Tommy, that was excellent. Okay. Does anyone have any questions about what Tommy just presented that they'd like to ask to Tommy? And I have a couple if Tommy's willing to. Okay. Tommy, do you want to chat about it a little bit more?
Okay.
Okay. So the presentation was amazing. Can I let's try to dig in even further what's going on. So you on the first slide you proved that very nice result that so now you've shown it's a good kernel. You can apply, like you said in the first page, once you know that, you have now in fact, if you have a continuous function, you have uniform convergence of the Feher kernels convolved with the function back to the function itself. Right. So like you said, we don't quite get it for the partial sums of the Fourier series, but if we take this, if we do this averaging, we get convergence even for continuous functions. Right. All right, so let's look. So we looked at what was different between the Feher kernels and the Dirichlet kernels as functions. Mm-hmm. Could we try to see what's different about them if we look at their Fourier series, their Fourier coefficients? So does that make sense? Can you write the Dirichlet kernel down just on the bottom of your page?
Oh, yeah.
Let's try it for the Dirichlet kernel, and then I can take over if the Feher kernel is a little bit tricky to see.
Yeah.
Okay, so this is the Dirichlet kernel, but for the ANs are just equal to 1, right?
Yeah.
Yeah. And it's a sum from minus n to n.
Yeah. Right. So n includes yeah.
All right. So like you were writing those ANs there. But so what are the Fourier? And I told you they're equal to 1. So what are the Fourier coefficients of the Dirichlet kernel? If I think of the Dirichlet kernel and try to write it as a Fourier series, what are its Fourier coefficients? This is kind of a trick question.
Okay, I feel like it should have, like the first thing that came to mind is 1, but I feel like
yeah. Okay, some of them are 1, right? You're spot on. So which ones are 1? And this is again like you've already said it. You've already like for the so they're all one, right? Except for but a Fourier series is an infinite sum, right?
Mm-hmm.
So if I were to write this as a Fourier series, um, I would have ones. The f hat n's are one for absolute value of n less than or equal to capital N, right?
Mm-hmm.
And then they're all equal to 0 afterwards.
Yeah.
So this is in fact a trig polynomial. Um, and so the if it's so the Fourier coefficients of the Dirichlet kernel are equal to 1 or they're equal to 0.
Mm-hmm.
And could you draw like a graph of those? So just like what would look like as a graph over the integers? I've never done something like this in class before, so I can do it if the question doesn't make sense. Does that make sense?
So you're saying not the graph of the actual like Dirichlet kernels, like
but just the coefficients, yeah, on the Fourier side, so sort of.
Okay, like for like multiple values of capital N.
Just pick a pick one capital N, and then I just like like we just said, some of them are 1 and some of them are 0. I just want to get a picture of that. Right. So if I fix capital N,
right, then they're all 1.
So it's like, no, I this is really tricky because we haven't done anything like that. Yeah. Let me so I think this is and then it works. So so they're all I'll draw the picture because I'm gonna draw it anyway. But this is, I claim that there's a cheap way to think about all of what Tommy just told us. So here was a Dirichlet kernel. I'm just going to write. This is e to the I and x. All right, and if I think of it as a Fourier series, so then d hat n of n is equal to 1 if absolute n is less than or equal to n, right? Because I just have a 1 there, and 0 if absolute n is bigger than n. So this is this is a funny question that I asked, and I didn't expect this to be obvious at all. So there's something. So the function looks like this. So here's 0. Say here's minus n. Here's n. I don't know if it should have drawn it symmetric on both sides. Approximately symmetric, and then they start being 0, right? Here's n plus 1. Here's minus n plus 1. So so it looks like this is the graph of the Fourier coefficients. And if I were drawing it, if I just were pretending that this was a continuous function, not a function on the integers, it would look like this. Maybe I could use a different color. All right, now Tommy, back again. I'm sorry to be picking on you. What type of is this? What are some things you notice about this function?
Not continuous.
Exactly. Yes, it's it has a jump, right? The Dirichlet kernel. If I think about its Fourier coefficients, there's a jump, right? They're 1 and then they're 0. So somehow, and at the beginning of class, I said there was going to be this relationship between smoothness of a function and decay of its Fourier coefficients. But and we saw that like if you had a C2 function, then the Fourier coefficients were nicely decaying. But it turns out that this relationship goes both ways. Um, the the smoothest properties of the on the Fourier side of if I view the Fourier, if I just take a function and plot its Fourier coefficients and then look at what type of function over the integers, I mean, I have to play like a little bit of a loose game here because it's just a function over the integers, so I don't really want to talk about its smoothness. But here I see that there's like it looks like there's a jump going on. Something if I kind of filled in the lines, this is not, as Tommy pointed out, it does not look like it's not a continuous function. So I claim that there's a game going on where this smoothness and decay, there's also a vice versa, like smoothness of the Fourier coefficients, and then decay properties of the function. And if like we dig down to the heart of what went on, like as Tommy just showed us for the Dirichlet kernel, the problem, right? It failed to be this good kernel because its integral was divergent, so the function didn't have good decay properties, right? The integrals grew like log of n. So what happens with the fair kernels?
Yeah, so does that mean that the fair kernel when like n is absolute value of n is less than or equal to big N, it's going to be 1 over n, so it like connects as like n goes to infinity?
Exactly. Yeah. So like what's going exactly right at the end, right? Right when it's I'll plot the fair kernels now. But Tommy's exactly right. Like where it's going to fix this sorry, I think it's a grocery delivery. I don't know how do I stop it. Oh, here, I was pressing the wrong screen. I'm going to plot the Fayer kernels. So the Fayer kernels, so f of fn of x is equal to 1 over n, sum from n equals 0 to n minus 1. So we take an average of the Dirichlet kernels, dn of x. And so if I want to compute the Fourier coefficients, I can use linearity of like the integral, right? So when I put this hat on, I'm multiplying by e to the minus I and x and taking integrals. Maybe I have too many n's here. Sorry, I've messed this all up. I'm going to use a k. This is 1 over n, k equals 0 to n minus 1, d k hat n. And as Tommy just did very quickly in her head, this is now this has a different graph. And let me just draw it. It's so remember what's going on. So these are either this is 1 if n is less than an absolute value than k, and 0 otherwise. And then I have this big 1 over n out front. So I don't expect this to be obvious if you haven't been playing with the computations, but what the Fayer kernel looks like is a triangle. So at n it's at 0. At 0 it's 1, just like the Dirichlet kernel. And then by the time I get to n, they've come back down to 0, and there's 0 afterwards. So I think the formula is 1 minus n absolute n over n, and then the plus. So if this function 0 if little n is is bigger than capital N. So the Fair kernel smooths out the Dirichlet kernel. Like you said, it's taking we're taking an average of the Dirichlet kernels, and so it smooths them out. And then what Tommy just proved is that this is great. You get better decay properties on the other side. So we saw that instead of having on the denominator before, so you had 1 over n out front, and instead of having 1 over n decay, we got 1 over n squared decay kind of. So let me write this as a bound. It's a bound. So I'm gonna rewrite the things from Tommy's slides so I have them on here. So this is equal to another formula this is the formula Tommy proved. Sine of nx over 2 squared divided by sine of x over 2 squared. Did you get that right? Yes. And then we know that this is positive, and in fact, it's less than or equal to some constant n to the -1 times the minimum of n squared and x to the -2. So that's the big gain, is that I have this x to the -2 outside, so I no longer have that log 1 over x. When you integrate 1 over x, you get a log. Here I have 1 over x squared. And I have and then my other property, property B, I'll call it, is what I just had, what I just wrote down, is equal to 1 minus should look like a 0. Okay. Okay. So these are so I have these two bounds. Okay. And also just rewrite the result that the main theorem that Tommy proved after applying the fact that after proving that the failure kernels form a good kernel, good family of kernels, you have uniform convergence back to the function itself. So here's the theorem. If f is C0t, it's C0 in the torus, then, actually, let me, hold on one second. I'm just gonna introduce some notation. So I'm gonna define sigma n of f is equal to f convolved with the Fair kernel. And this is, as we saw, this is just equal to 1 over n of n equals 0 to n minus 1 Sn S little n f. So remember, Fair kernels were produced by taking an average of the partial Fourier sums. So so this is, I'm going to call this operator sigma n of f. It's taking its partial Fourier sums and then averaging them out. Yeah, this is these are also called the Cesaro means of f. And the theorem that Tommy proved is the following. So if f is a continuous function on T, then sigma n of f, the Cesaro means of f, converge to f uniformly. And I'm going to write this in the notation we introduced, I think, last time. If I measure the sup norm of the difference, this goes to 0. So this, or the uniform norm of the distance. Okay. And using this fact and the fact that the integral over from minus pi to pi is a finite integral, I also want to emphasize one other form of convergence that we also obtain here. Moreover, the integral from minus pi to pi let me put some x's in here. And why is this? Well, I could just take supremum inside the integral. I could just take absolute. I could just take a supremum of the integrand, pull that out, and use this fact. Use that this goes to 0, and then I'm just left with a multiplying by 2 pi. So I have 2 pi times this after taking. So in fact, this is a this convergence implies this convergence, right? And I want to use some notation for this. I want to define this as, so I want to define the L1 norm of a function is given by just its integral. The absolute value of its integral. So this up here, this means I have convergence in L1. Okay, so just like I wrote this convergence, this uniform convergence as convergence in the sup norm, this convergence of the in its integral sense, capital L1 convergence of the Cesaro means. Okay, so this is what Tommy just proved, right? Because we could just apply the good kernel lemma to the Cesaro means. All right, so
Professor?
Yes.
You said something in here. Some statement here depends on the minus pi to pi being a finite interval. Which statement of that?
The fact that this. So I'll put in an implication. So this implies this.
Okay, that step needs the compactness.
Yes. Right, because I could just I want to prove it. I want to throw out. I want to just take the supremum of the integrand, and then just I bound the integral by the supremum of the integrand times the length of the interval. And since the length of the interval is only 2 pi, then I get convergence. Does that answer your question?
Yeah.
Okay. Okay.
How does the Poisson kernel fit into this picture? Because you kind of have.
Sorry, Michael, you froze. Is Michael frozen for everybody or just for me? For everybody. Okay, Michael, let me answer your question if you can hear me, but I can't talk by just saying we're going to get to the Poisson kernel in a bit, so we haven't introduced it yet. but it's going to be an even weaker convergence in an even weaker sense. And we'll actually flesh that out a bit more during office hours on Thursday too. So Michael, if your connection improves, just interrupt me if you want to complete your question.
Quick question about L1 norm.
Yes.
Do you want to put in 1 over 2 pi there, or is this okay? I mean, it probably doesn't matter much, but just asking.
Let's decide. Let's do it. Let's put the 1 over 2 pi in there. Yeah, let's do it. Because it'd be nice if the function 1 had norm 1. Let's do that. And then let's put 1, 2, or 2, just for fun. Okay. All right. So this should seem kind of a little academic at the moment. Like we just sort of we decided what was the really important problem was considering the partial Fourier sums of a function and trying to prove convergence properties, and then we just we said, oh well, that's not a good kernel. Let's modify the DNs by doing this procedure to its Fourier coefficients. Let's introduce these Fayer kernels. Let's do this averaging, and then we get good convergence properties. Okay, so what? The point is that we can now reap some consequences, and some of the things we were worried about last time, we had to fight for before, are going to become a lot easier, and we can prove some new results. So let's deduce a few corollaries of this theorem, and I'll try and convince you that even though it looks kind of we just changed the question we were interested in, this is actually useful. This is actually a useful theorem. So corollary 1 is we can uniqueness again. So we can take f a continuous function on T, then if the Fourier coefficients are all 0, this implies that that f is identically 0. And the proof is easy now that we know this bit about the Cesaro summability of f. So by assumption, just rewriting this. So from the assumption, we know that all of the Cesaro means of f are equal to 0 for every n, and converges to f uniformly by the theorem, right? So we have a sequence of just consisting of the 0 function, 0 function, 0 function, converging to uniformly to f. So f has no choice but to be the 0 function too.
F question.
0 function. Yes.
Does it break if we no longer know if it converges uniformly? Like, this is just kind of hypothetical, but suppose we only knew that the Cesaro sums converge like pointwise. Does this still work?
Let's see. So it worked at points. Well, okay. No, I guess. Right. Let's see. No. It's okay, right? If we had the sequence and we know we had pointwise convergence, right? Then we just pick a point, and show that f of x is equal to 0, right? Yeah, sorry about that. I tripped myself. Here, like just pointwise convergence is enough, right? Since everything in the sequence is a zero function. Um, yeah. Okay.
Sorry, quick question.
Yeah. You're
So
back. Okay.
yes, my internet died. I don't know how much of my question got through last time, but so like how does the Poisson kernel fit into this? Because like if you look at it in the dual space, it will like kind of have exponential decay instead of like
Yeah.
whatever
So
is yeah.
yeah. So okay. So we'll get to the Poisson kernel in a bit, but you're right that something even we're going to make the kernel even better somehow. Um, when we introduce the Poisson. So we haven't introduced it yet. So
Okay, yeah.
so there's and we'll flesh this out a little bit more maybe at the end of this class if I get to the Poisson kernel. And then you'll definitely flesh it out more in your homework. Is like the type of summability is even weaker than so we just replaced like summing an infinite series by Cesaro summing an infinite series, which is like this average. So we have a sequence, and then we consider its average of its partial sums, and then ask for a convergence of these averages. That's the Feher kernel does that, and we get that's Cesaro summability. And then there's a notion called a Bell summability, and that'll give rise to the Poisson kernel, even an even kind of looser form of summability. And we'll see. So that's somehow the weakest the weakest version of this. So meaning so what I mean by weakest version, I mean we made the question easier. We made the game a little bit easier for ourselves by introducing this Feher kernel, and then when we introduce the Poisson kernel, we're going to make the game even easier somehow. And then yeah, but this will be this looks a bit random, right? That we just decided, okay, take the Dirichlet kernel. What happens if we smooth it out and make a triangle? And okay, as I'm going to try and convince you, this isn't. It ends up not being a bad strategy to see what happens when you convolve your function with different kernels. And we'll have a couple of other different kernels that we'll consider in the class. So yeah. And hopefully, but after a while, this all won't seem so random. Okay, so the corollary we just proved the uniqueness theorem, and if you remember the proof from last time, this is a lot easier. So that's one benefit. But here I'm going to try and show you something new. So another corollary is something new, and this is the density of trig polynomials. And this is a deep theorem, deep corollary. This is deep and new. We don't know this fact yet. So the corollary is that trig polynomials are dense in C0 T. And in fact, in L1 of T. Sorry, maybe I should say this as in space of Riemann integral functions. Integrable functions under the norm L1. Under the L1 norm. Okay, so how do we prove this? Well, we're just going to apply the convergence result we just considered about the Cesaro sums of a function.
When you're talking about the density in C0 of T, yep. What norm is that? Is that also the L1 norm?
No, under the supremum norm.
Okay.
So we'll often use the supremum norm when we talk about the continuous functions as a vector space. Um, uh, um, yeah, but I should specify. You're right. Thank you, Michael. Okay, so the proof. Or maybe I should say what this means first. So if f is a continuous function on the circle, this implies for every epsilon bigger than 0, there exists a trig polynomial p of x such f minus p of x, f minus p, sorry, is less than epsilon. So you give me an epsilon and a function and a continuous function, and I can find a trig polynomial that's epsilon close to that function in the supremum norm. And the proof. Actually, can anyone guess the proof? Which trig polynomial am I going to use to approximate f?
If you convolve it with the Thayer kernel, then you're going to get a trig polynomial that's as close as you want.
Exactly, right? Exactly. So, sigma in f is a trig polynomial. And for every n. And so whatever epsilon you take, I could just the trig polynomial I just convolve with the Thayer kernel. So sigma in f. Remember, this is k. Fn convolve with f. So those are trig polynomials. Yeah, and in the L1 topology, it's the same proof, just using this statement of the theorem. So the same thing tells us I have density in amongst the Riemann integrable functions in L1. Okay, and then a last corollary for now is the following. So this is called the Riemann-Lebesgue lemma. And you should already tell that this is something deep because it's got two names on it. So this is a corollary of the previous theorem we just proved. So the Riemann-Lebesgue lemma says that if f is in C0T, then as n goes to infinity. So the Fourier coefficients go to 0, which is something we didn't know before. And this is true, in fact, for f just Riemann integrable. So if f is just a Riemann integrable function, its Fourier coefficients tend to 0 as n goes to infinity. Okay, this doesn't come with a qualitative rate, but yeah, and a side corollary of this, if f is C2 T, this means that we're C1. Why did I jump to C2? C1. This implies that is little o of 1 over n. So it goes to 0 faster than 1 over n. The way you prove this, the second bullet point, is of course the Fourier coefficients of f prime, which f prime is now a continuous function and has Fourier coefficients tending to 0, and the Fourier coefficients of f prime are just given by in times the Fourier coefficients of f. So then you can go on. If f is ck, then the Fourier coefficients to k like are little o of n to the minus k. So this is the Riemann lemma. Let's prove it. So the proof, again, it's going to be quick given what we know about the Thayer kernels. So just give it. So given epsilon bigger than 0, find n such that we're going to try to say that we're going to try and prove a convergence statement, which means we're going to try and say for any epsilon, I can find a capital N such that if little n is bigger than capital N, then f hat of n is less than is an absolute value less than epsilon. Well, what can we do? Given epsilon bigger than 0, find a capital N such that sigma n minus f, sigma n of f minus f in L1 is less than epsilon. So they're integral. They're the absolute value of their integral. The integral of their absolute value is less than epsilon. Okay, but for every n absolute n bigger than capital N, sigma n f hat, this is a trig polynomial, right? And I drew you the right. It's a triangle that has its bases with 2 capital N. But if little n is bigger than capital N, it's 0 forever after that. So so we have this. So f hat n in absolute value is equal to f hat n minus sigma n f hat n, right? Because I'm just subtracting if sorry, I should. If little n is bigger than capital N. And what are these? This is equal to 1 over 2 pi f of x minus sigma n f of x e to the minus I n x dx, right? So this is less than or equal to if I measure the absolute value of these difference of Fourier coefficients, this is less than or equal to the L1, the norm of the difference between the functions in L1, which I know is less, which I cooked up to be less than epsilon. So that's this clever proof for every n bigger than capital N. This is a clever proof of the Riemann-Lebesgue lemma. It's just noting that, well, I can get as close as I like to f in L1 by taking its Cesaro mean, and then just noting that this is a function with 0 that has has 0 Fourier coefficients for large n. So I'm close to f for a function with 0 coefficients, so the Fourier coefficients of f have to be small, in fact, too. Does this argument make sense?
How did you get from the second quantity to the third quantity to the integral?
So from here to here?
Yeah.
So that's just equality. I just wrote down the definition of the Fourier coefficient, the nth Fourier coefficient of f. It's just the integral of f multiplied against e to the minus I n x. And I did the same for this. It's just by definition. And then I combine the I had 2 integrals and I combined them to be one. Since they each had the same integrated against the same weight, this guy.
And then after that, you like move the absolute value into the integral. Is that what you did?
Exactly.
Okay.
Yeah. After that, I just took the absolute values, threw them in, and then I noted that this has absolute value 1, right, for every n.
I've got a quick question for you too.
Yeah.
So I'm just trying to make sure I followed every step here. So the first thing that you did was you took n big enough so that you could find, so you could kind of approximate f with the Cesaro sum. Is that correct?
Exactly.
Okay. And then you noted that after, for every little n, I guess bigger than that big N, you have that's 0. So then you can write that Fourier coefficient as the difference. Okay.
Yeah.
Got it.
Yeah. This is just 0. So
yeah.
I just subtracted 0, and then I rewrote it in a way, and then I destroyed that by putting absolute values in. But the damage is done because I know that this is small.
Because you constructed it such that you could do that. Yeah.
Yep.
This is a clever argument. Thanks.
Yeah. This is really clever. Okay, and now the next one more nice consequence, and you guys are going to hate me for this one, even more than I think from the uniqueness, the easy uniqueness proof I just gave. But it's all I gave some technical arguments because I want because somehow somehow you can appreciate what's going on, and this is all a bit clever. Okay, so the theorem I proved last time, this very difficult technical theorem, I'm gonna do some tricks with the Fair kernel and make that proof super easy too, or super short. No, I'm not gonna make it super easy. I'm gonna do it quickly. So the theorem from last time. Via Fair kernel tricks. Theorem. So suppose 0 alpha is less than or equal to 1, and suppose f is in C alpha. So alpha is Holder continuous with exponent alpha. Then, as we showed before, I have S in F minus F in L infinity. I have uniform convergence of Okay, so note here I have this is a theorem about the Fourier sums, but I'm going to make use of my knowledge of the nice behavior of the Fair kernel to prove this result. Okay, so the proof is we're going to start with I claim that if I know more about F, so if I know something about the smoothness of F, if I know this in particular, I can beat this. I can turn this qualitative statement from the theorem that Tommy proved at the beginning of class into a quantitative statement. So I can tell you exactly how fast this goes to 0 in terms of n. So first we claim that I'm going to call this star sigma n of f minus f in L infinity is less than or equal to some constant times n to the minus alpha times the C alpha norm of f, which is just a number, right? We're assuming f is in C alpha. This is just a number. But so I know this thing goes to 0 from the theorem that Tommy proved. But now I claim that if I know more about f, I can in fact I can give you a rate. I can give you a rate of convergence. It looks like n to the minus alpha, where alpha is the Helder exponent for f. Okay, so how do we prove this? So let's prove star. Okay, so sigma n f minus f and L infinity. This is equal to the sup over all x in t of sigma n f of x minus f of x, which is equal. So now I'm going to remember that this is sigma n is convolution with the Fair kernel. I'm also going to remember the Fair kernel integrates out to 1. So this is equal to the sup sin t of 1 over 2 pi times the integral from minus pi to pi of f n, f capital N, y, f of x minus y minus f of x dy. So here I'm using the property, the first property Tommy proved was that 1 over 2 pi f n of y dy is equal to 1. Okay, so that I have this equality, and then this is less than or equal to, I'm going to use the bound that I had before. So minus pi to pi. I'm going to use the fact that I'm going to argue similar to last time, and I know that, and this is just, I know that f is in C alpha dy, which is less than or equal to the.
Sorry,
C
I have a quick question.
Yeah.
I was just writing something down and I kind of missed where you wrote use that integral integrates out to 1 for the Fair kernel.
Yes, to get this equality. So how did I get from here to here?
Yeah, sure. Yeah, I guess that's what I'm asking, I suppose.
Yeah. So I rewrote. So this is that turned into this integral. Just the definition of the Fair kernel convolved with f.
Yeah.
And then I also rewrote f. I rewrote f as 2 pi minus pi to pi k and y f of x dy. So I just threw f of x. I just multiplied f by 1 and then threw the f of x, which
sure.
And then I combined the two integrals here.
Sure. So I guess your kn would be fn.
Sorry, fn. Yeah.
Okay. No, that's okay. I see what you mean now. Thank you.
This should be fn. Yeah. Yes, fn. Okay, and now I pull the C alpha norm of f out, and I'm just going to use my and this I'm going to forget about constants, minus pi to pi, and I'm going to use the bound that I wrote down on the first slide for. The Fair kernels were bounded by the minimum of n and 1 over n times y squared, and then I have y to the alpha dy. And this bound is from the very beginning of class, and it follows from the formula. The first thing that Tommy did was prove a nice formula involving signs for the Fair kernel. From there, you can easily deduce this bound, or not easily, but you can deduce the bound from there. Okay, and so now I have to choose when do I use n and when do I use 1 over n times y squared. So let me just do a side computation. So n is less than or equal to n minus 1 times y to the minus 2, if and only if y squared is less than 1 over n squared, just algebra, if and only if absolute y is less than 1 over n. All right, so so this tells me I should split the integral into two pieces. Or I'm going to split the integral into the pieces depending on whether this is smaller or this is smaller, and the splitting happens for y less than 1 over n. So this is all less than or equal to C alpha norm of f times integral of y less than 1 over n. And then here I have, don't forget the y to the alpha, so I get y to the alpha times n dy, and then plus the integral when y is bigger than 1 over n and less than pi, of course, in absolute value, times n to the minus 1 y to the minus 2 plus alpha dy. And now I can just do these integrals. So I get this, for this top one, you see I have n times, and then I have n to the minus alpha, minus alpha plus 1. So I just get n to the minus alpha here. And then for the second integral, I also get n to the minus alpha. Roughly, up to a constant. So this is less than or equal to. Okay, so this is nice. If I have, I know how fast the Cesaro means of f converge to f if I know a little bit more about f. So if I know if f is C alpha, then I have a rate for convergence. So I've proved. Let me just rewrite it again. Like this. Possibly a constant there. Another constant. Okay, now here comes the trick. Remember, I'm trying to prove what we're trying to prove. I'm trying to prove that, in fact, I have uniform convergence of the partial Fourier sums if for a C alpha function. And so I want to, and then somehow I'm going to try and use this knowledge about Fair kernels, and I'm going to try and relate the Fair kernels to the partial Fourier sums as follows. So the trick, which will take you a million years to come up with, this is just equal to this. If I take the partial Fourier sums of the Fair sum of f, I just recover back this Fair sum, the Cesaro sum. So that's an identity, and then hence, this difference is equal to Sn of f minus sigma n of f plus sigma n of f minus f. So I added and subtracted this. But it's also equal to this. All right, now that's now I'm in business, because I know something more now, right? I know that I know that this piece goes to 0, right, as n goes to infinity. So that's great. And I've introduced that piece at what cost? At introducing this piece, this first piece here. And this to me now looks a little scary, right? If I just look at it, because, well, I have this nice thing going to 0, but remember, I have basically I have bad control over the Dirichlet kernel, right? In fact, if I think of this as then like there's an integral here, and so I have something growing like log n times something that goes to 0. So I'm toast, right? If I don't know how fast this thing goes to 0, because I know this thing is growing like log n. But that's why I just went through this. That's what calls for a quantitative estimate. So up here, I have in fact that this business is going to 0, like into the minus alpha, where alpha is a positive number. And so I'm going to fight with, so I'll prove this in a second, but the fight is going to be between into the minus alpha from this factor and log n from this factor, and into the minus alpha wins. So this is going to go to 0. So that's the game. So let's see it play out. So this is equal to, let me write this again. This is equal to Dirichlet kernel convolved with f minus sigma n f plus sigma n f minus f. So these two pieces. Let's call this 1 plus 2. And for 1 is a tricky piece, right? I know that 2 goes to 0. But 1 is less than or equal to, well, this is what? This is the integral from minus pi to pi dny. And then I have f minus sigma n of f x minus y dy, which is less than or equal to, I can just take supremum over x and y of this guy here, and that I know that goes to 0. So this is less than or equal to f minus sigma n f in L infinity in the sup norm times, and I'm left with just the integral of the absolute value of d and y. I'll write that as fancy notation as the L1 norm of dn. And that's less than, this I know now is less than n to the minus alpha times the alpha norm of f. And then this we proved in your homework that this is like a constant times log n. I have an upper bound like that. So this still goes to 0. As long as alpha is positive, a positive number. And then the second piece, we know the second piece, right? So in 2 is equal to and we're done. So this proof was a lot cleaner, right, from before, but it somehow required a lot of ingenuity. First, you would have had to, like, if you imagine trying to discover this on your own, first you would have had to think about averaging the, creating these Cesaro sums, thinking about the definition of what, this good kernel theorem, etc. And then this clever business here, like there's a lot of kind of magic going on in this argument to prove this theorem here, the argument that I just gave right now. Whereas before the argument I gave was really technical and required some like mastery of like chopping the integral into pieces and using one bound here, using cancellation somehow, right? We needed to exploit cancellation somehow, but we couldn't integrate by parts. The other proof was kind of technical, but somehow, like, if you sit yourself down at a chair long enough, you'll figure that one out. Whereas this one is, I think, is a little trickier, and it involves some magic. So anyway, for me, it's often really nice to know both arguments, or be able to prove something in a couple different ways. I'm kind of convinced I could remember how to do the other proof if you give me long enough, possibly a couple of days. But this proof, I feel like I would I forget every year, and then remember it when I teach a class. So. Any questions about this?
Can I ask a question about something that we talked about closer to the beginning of class?
Yeah, of course, of course.
So I'm sorry if you said this already, but you mentioned a couple times that the Fair kernel is in some sense smoother than the Dirichlet kernel, or the Fourier series is smoother.
Yeah.
But I didn't quite catch what your sort of meaning of smoother was over the integers.
Yeah, it's a little bit tongue in cheek, right? But you see, here's the so I don't smoother, right? If I view them as functions over the integers, but if I just draw the graph, I see here that there's a jump, right?
Yeah.
There's a jump. I go from 1 all the way down to 0. I go from 1 to 0 immediately, right? So that's my discontinuity. Whereas for the fair kernels, I smooth out that jump.
Okay. I mean, obviously, we can pick apart that argument as not rigorous, but
yeah.
So I guess maybe we're not ready to hear a more rigorous way to think about it, but is there some? Okay.
No. I don't mean shaking my head. By more rigorous, this is the rigor. Yes.
Because I guess you can draw a continuous function for the Dirichlet kernel too, that just connects the 1 to the 0 across the blank space.
Oh, okay. So okay. So let me okay. I guess let me just argue like this for the time being. This relationship, okay, the relationship between smoothness and decay, and like decay properties or integrability properties, going both ways is going to come up a lot during the class. And here it looks like I'm faking it a bit, right? Because like you said, these are functions over the integers, so it doesn't look like one is necessarily smoother than the other, right? That's your objection, right?
Yeah, well, yeah. If your argument is that your continuation of it across the reals is continuous, like of course you can always draw continuous.
Yeah. So that like drop that argument, but instead just like look at the two graphs just as functions over the integers. There's a way in which this guy looks better than this one, right?
So should we be thinking about it like as the change between adjacent Fourier coefficients goes to 0 as n gets large?
Yeah, which is like the derivative, right? Right.
Yeah, even though it's not really continuous for any particular.
Yeah, so maybe forget about the continuity and just think about like the derivative, sort of, right? If I think about what's happening for what's happening here, the jump, there's a jump between the size of the Fourier coefficients here, right? And so that's what I mean by like kind of lack of smoothness. And here there are no jumps, right? There are no jumps. So the Fourier coefficients vary. They vary smoothly, very vary, smoothly, and later on we're going to do we're going to consider functions on the line instead of functions on the circle, and then we're consider the Fourier series of such functions. The Fourier transform of such functions, which will be another function, and there there's going to be the back and forth is going to be really, really apparent because they're both going to be functions. A function is going to be a function, and its Fourier transform is going to be another function, and we'll have this explicit relationship between smoothness on one side and decay on the other side. Here, it's not quite so precise, but you can kind of. I'm trying to emphasize you can kind of see it happening. The one way it's very precise, like the smoothness of f corresponds to the decay of Fourier coefficients. That was an easy relationship, right? We saw we're seeing it over and over again. Like if you were C2, then you decay like 1 over n squared. If you're CK, you decay like 1 over n to the k. So that direction looks nice. This direction we have to kind of like suspend rigor a little bit to see the relationship. But the point I'm trying to make is there is a relationship. And next time we're going to talk about one additional kernel, the Poisson kernel, which will be even smoother. But yeah, excellent question. This is
satisfying for me. Thank you.
It's not. Yeah.
Thank you.
Okay. This is a good place to stop, actually. Too. So well, and it's also 3:55, so we have to stop. So thanks. Thanks again, Tommy, for the excellent presentation. That was absolutely perfect. And thank you again. Thank you for going first. So please, I'll have more in-class lectures. Please volunteer. I know I'm going to make it a little scary, like at the end. I promise I'll make it scary for. I'll try to make it equally scary for everybody. But there's like, it's okay. It's meant to be that way. All right, guys.
Thank you.
Bye.
Thanks.